Welcome. It's great to see everyone here. This is our first postdoc doubleheader of the year, where about once a quarter we have 2 talks given by postdocs either on their research here at Stanford or when they are new to the community on their awesome work from their PhD. So our first speaker for today will be Adam Shaw, who was a doctoral student at Caltech with Madeline Andres on some really interesting experiments, sort of exploring, I would say almost for the first time, the promise of quantum simulators to really deeply study questions in quantum information science that were hard to just fully access in theory. So he's going to tell us that story, and
thanks, John. Thanks everybody for being here. As John said, did my PhD with Manuel, and now started my postdoc with John just as a month ago. Excited to talk about this year and sort of learn new things and get into new collaborations as we go on. And in general, my talk today will be actually largely theory, but I'll have lots of experiments sprinkled throughout it on how we can use chaos, learn noise, and analog quantum simulations. I am an experimentalist, so I do quickly want to give an overview of the experimental platform I'll be talking about today, which are systems of optical tweezers, which are tightly focused laser beams to trap a single atom. You can then bring many of these laser beams together and create large-scale arrays in 1 dimension, 2 dimensions, or even 3 dimensions. And the reason that we care about these systems is because then when we bring atoms close together, we can make them interact with each other via distance-based Rydberg interactions, where if 2 atoms are far apart from each other, then they basically don't see each other, there's no interaction. But as we bring 2 atoms close together, the Rydberg blockade effect means that the atoms can't be in the Rydberg state at the same time. And so when we excite them to the Rydberg state with a global pulse, we instead get 1 excitation shared across both atoms, very naturally realizing this form of a Bell state here. And then we can control this interaction from kilohertz to gigahertz just by adjusting the spacing between the atoms. In our lab at Caltech, we studied this and have achieved sort of the state-of-the-art fidelity for making this Bell state on this Rydberg transition of just over 3 nines of fidelity. And detailed error modeling shows that 4 nines is experimentally realistic with these systems. Now, I'm not at all trying to suggest that we're the only ones in the Rydberg atom ray game. In fact, there's lots of people that have been doing lots of work on Rydberg atom rays for the past several years. This is really just a small selection of the various types of topics that have been used to study. And if you just look at archive submissions, the number of papers have been growing exponentially in the last few years. It's a quite exciting time to sort of be in the field and think about this new type of platform, which a few years ago I think was thought of as sort of a third candidate in the race for a quantum computer, quantum simulator, but now is really talked about on the same footing as trapped ion and superconducting circuit systems.
There's been 100 papers already.
Yeah.
This year.
Yes.
No, this year.
Yeah. No, and if you believe this little dot here being a little bit higher, the exponential is increasing in its rate, we'll see what happens.
when will there be more papers than added?
I think we'll have to wait a little bit there. Extrapolate to 3,000, Okay, so this is the sort of field that we're working in here. And one of the most exciting things about atom rings is that they can be used both for quantum simulation and quantum computation tasks. So here I'm sort of defining these also by the terms analog and digital. An analog quantum simulator is one which basically implements some natural Hamiltonian of the system and then watch it evolve over time. Whereas a digital quantum computer, we try to actually map computational problems into some dynamics that we highly engineer into the system. And both of these are things I've explored during my PhD and I'm happy to talk to people about. However, for today, I'm mostly going to be focusing on this topic of quantum simulation and how we can really sort of quantitatively study the behavior of analog quantum simulators. So the systems we're going to be considering are 1-dimensional chains of atoms of up to 60 atoms in this case. And we're going to imagine that we're evolving these atoms under their natural Ising-like Hamiltonian, shown here. And if we do this with no errors, the output of the state will be some pure state psi here. And the key characteristic of the state is that its entanglement entropy saturates the volume law entangled level in linear time, which is hard to simulate using sort of standard tensor network type methods, which we'll return to later. Of course, this is not the actual state that we output from our experiment. Because we always have noise affecting our system, the actual output of our experiment will be some noisy mixed state, rho experimental, which we want to characterize by basically looking at what is the overlap between this noisy mixed state and our pure state. In other words, what is the fidelity, which you can sort of qualitatively think of as the probability that we don't make any errors when we're executing our quantum operation. We were able to measure fidelity for the 2-qubit case earlier, but it turns out to be exponentially difficult to measure this for larger systems. Now, this problem has been around for a long time, and in fact was tackled several years ago, because it turns out that if you explicitly randomize these dynamics, and you then measure these different states, if you measure these different states, psi and rho experimental, in a single fixed basis, then you can actually show that you can estimate the fidelity with extremely good accuracy and precision. This was the key fact that was used in Google's claim on supremacy in 2019, this fidelity estimation protocol. Now, this requires that these dynamics be explicitly randomized, whereas here we're talking about something which is a fixed deterministic Hamiltonian evolution. But over a series of subsequent papers, we show you can actually apply the same logic to the Hamiltonian system. And in fact, this gives a new understanding for how Hamiltonian dynamics can actually be related to digital and in fact random dynamics of quantum systems. It opens up a whole new door of analysis for them. We'll go over that in the next couple of slides here. So to start, I basically just want to look at how this looks if your dynamics are randomized. So here's essentially the fidelity estimation formula, which is used in Google's quantum supremacy work, etc. This is the linear cross entropy shown here, which is essentially proportional to just the cross correlation between the bit string probability distribution that you measure from the experiment versus the one from the theory. Here. And we can compute this thing for our experiment, our Hamiltonian system as well. And so, for instance, what we can think about doing is we can take our experimental system, or a simulation of our experimental system, which starts in a single fixed basis state. We then evolve it with our Hamiltonian, and then we're going to look at how this probability distribution changes over time. And you can see that there's initially some coherent dynamics, but very quickly this probability distribution becomes effectively random in this basis, and just looks like something without any sort of coherent procedure to it. This is really the flow. The spectral pattern is a quantum fingerprint of the dynamics. We can see that because now, if I copy over my state, but now I apply a phase flip error on a single qubit, initially that does not change the distribution because it's invisible in the computational basis. But if we now continue the evolution, after a very short amount of time, these distributions become entirely distinguishable. You can really think about this as sort of a quantum butterfly effect, where small changes in the state in terms of errors lead to large changes in the output distribution. And this fact means that we can look at cross correlation between these two different distributions as a very good estimator of fidelity. This works if the dynamics are explicitly randomized, but the problem is now, if you're thinking about a Hamiltonian system, there are residual correlations which can exist because of things like energy conservation or symmetries of your system. So for instance, the easiest way to think about it is that if you have some large detuning in your Hamiltonian, that will bias both your Q and your P, to have very few bit strings with ones in them, for instance. And this will then introduce correlations between these two different distributions, which will bias the fidelity estimator and generically make it not work. So we're going to look at how we can get around this problem and actually how we can apply this still to analog quantum simulators. To understand that, we first have to sort of go into a little bit more of the math of random state ensembles and why this sort of fidelity estimation works. Why is it that randomness is important for us here? So we're going to consider some randomized dynamics where we take some initial state, we then apply some randomized dynamics, random unitary circuits, for instance, and then that outputs some random final state decided here. If we repeat this many times for different choices of randomization, and we look at how these states sort of scatter across our Hilbert space, they'll be distributed roughly uniformly across the Hilbert space. We could then think about measuring each of these states psi in a fixed basis, getting this probability distribution as we had before. And if we then look at how the probability of a single bit string changes as a function of our randomization, we'll again see some random distribution, but the key fact of random state ensembles is that if you look at the histogram, essentially, of all of these different probabilities, this follows a universal form, this exponential distribution. Also, the experts know the so-called Porter-Thomas distribution. And this is really the key hallmark of having a so-called par random, or just generically a random ensemble in a quantum sense. And like you have this exponential distribution, you can characterize this by its moments and see that the moments of random state ensemble follow this universal form. And this is the key fact that enables our fidelity estimation formula because it allows us to simplify a lot of complicated math about what is the exact dynamics happening in our system, and we just reduce it to these very simple principles of, well, things are going to look like these exponential distributions if we average them. Now we can look at how this changes and if we can recover the same behavior for Hamiltonian systems. So we're going to have some Hamiltonian system, starts with a fixed state, and then we apply some Hamiltonian, measure state psi t after. And we can then imagine looking at this trajectory in the Hilbert space, it covers some path. And we could then think, okay, how can we sample a random ensemble from this? Well, the first thing we could do, we could think about stopping this at different times. And we could ask, is this now a random state ensemble? Does it fulfill the same requirements of this Porter-Thomas distribution we saw a second ago? And clearly, you can probably guess the answer is no. Because if you look at a single bit string here and you look at it over time, you can see that if you then take the histogram of all these probabilities, you see something which is very far off from the expectation for a random state ensemble. And this is not unsurprising because effectively our affected Hilbert space size has been constrained by our symmetries and energy conservation. So we wouldn't expect to be able to get a random state for the entire Hilbert space. But the key fact is that we can characterize how constrained our Hilbert space is by this single quantity. This is rho diagonal. This is the diagonal density matrix, and it's essentially the time average of the quantum evolution over infinite time. And what I'll claim is that this quantity basically encodes all of the dynamics that sort of show where the state can move in Hilbert space. And what we can then do is we can look at what the overlap with this rho diagonal is with a specific bit string, called p diagonal z. And then it turns out that if we renormalize all of these p's, these probabilities by this p diagonal, then we recover this universal distribution for Thomas distribution. And it doesn't just hold for Rydberg systems. You can do this for Rydberg ions, trapped ions, XXD, which is in fact an integrable model. And you can see the same exact behavior. Then before rescaling by the p diagonal, you get something non-universal. After rescaling, you recover this exponential distribution. And you can recover these universal moments. And in fact, we can even see experimental evidence that these distributions emerge in global systems. This is a sort of surprising fact that I'm not going to be able to sort of motivate in full depth. I'll simply say that while sort of discovering these things, we actually sort of uncovered what we think is a whole new framework for understanding sort of quantum dynamics and analog quantum simulators in general, which we call Hilbert space ergodicity. I elaborated on in these two papers here. We're essentially for a very wide class of quantum systems, including random unitary circuits, but also systems that obey ETH, both interacting interval systems, with very weak assumptions. You can say that for any, if you take one of these models and you pick some random late evolution time, the state after that evolution time basically looks like some evolution specific thing multiplied by some universal behavior. What this really means is that we can factorize any quantum evolution in this wide class of behavior, the wide class of models, into some universal behavior, which is this random state ensemble, and some system specific. And the key takeaway is really that if we can analyze in this way, analog quantum dynamics doesn't have to be that different from how we analyze random unitary circuits in general.
Where do the conservation laws enter that question?
Conservation laws enter in rho diagonal. So rho diagonal will sort of encode all of the different conservation laws that you have in your system, because if it's sort of, it's like an identity matrix, then you have no conservation laws. But if you have any conservation laws, identity. Yes.
Is that formula how you normalize for distribution?
To get these things here, get these guys. Here we're just rescaling by the diagonal factor for all the individual p's, but it follows from this formula. That's right.
And this is numerical data on that?
This is numerical. Yes, this is experimental here for Rydberg arrays. This is numerical. But you can see this hold for all of these models, for Hubbard models, actually, which are not even non-integral. And so this is really a sort of very broad framework to understand a very wide class of systems, digital systems, and also. Okay, so without going into too many of the details, what I'll simply claim essentially is that we can take this fidelity estimation formula from Google, which taught entry from before, and there's some things that I'm graying out here which aren't too important, but the main takeaway is that if we rescale all of our probabilities by this p diagonal of z, we normalize away this average probability, it eliminates these biases and conservation laws. Maybe another way to say that is that essentially what I'm saying is that as long as you know the average probability, then you know that all of the fluctuations on top of that average follow this random state ensemble universal form, which enables fidelity estimation. It's probably easiest to show you that this works. So for instance, what we can do is we can take our experimental system in simulation. We can do it simulating with no error and also with our ab initio error model. I think it's a good form for our experiment. We can see that by comparing these two things, we see the fidelity estimator is a very good match for the fidelity across both system size and evolution time. And we can then put experimental data on this plot as well. And so you can create agreement between these three different curves that we really are able to benchmark the experimental fidelity here for system sizes up to n equals 30. I'm going to skip over a lot of details how we go larger than n equals 30. There are extrapolation methods that are used both in supremacy planes as well as our work. And I'll essentially say that we can then push this even higher. And if you look at the fidelity for creating volume law entangled states with our system, which you can see here, we can create a volume law entangled state of n equals 60 atoms with a fidelity of just about 10% in one dimension. And if you don't think about many-body fidelities, it's very hard to know, like, is this a big number, is this a small number? So I'll give a couple of points of reference on this. First of all, the silliest thing that you can say about this is that this is 17 orders of magnitude better than if we just picked a random state in a Hilbert space, which is silly, but still is like a big number, so it's nice to say. The other more reasonable things we can say is that we can do error modeling and we can show that to achieve numbers like this, you really need to have these 2 qubit fidelities of 3 nines that I was talking about earlier. This is highly sensitive to this fidelity, which I'll get back to in a little bit. And finally, as the last point of comparison, I'll simply say that when Google did their quantum supremacy work in 2019, there with the systems of 53 qubits in 2D, they achieved a fidelity over an order of magnitude lower. Now there are clear differences between these systems, one with a digital quantum processor, ours with an analog quantum simulator. But I think that the key takeaway here is that when you allow your dynamics to be more specialized and focused, you can achieve a higher fidelity at achieving those tasks. It really points to the future using analog quantum simulators to solve challenging problems, in my mind. Okay. We can then ask the question similar to how Google asked in the supremacy work of, how computationally difficult basically is it to replicate these experiments on a classical computer? Because both the quantum experiment and the classical computer have errors associated with them when trying to study these large scale systems. We can basically look at what the classical process for experts as a bond dimension looks like as a function of system size. And we can see that for the largest system size, n equals 60, requires a simulation time of something like 184 days to help that supercomputer. I'll quickly note that you might ask, are you sure you're using a good simulation algorithm for this? And I'll say that we tried many different simulation algorithms for this, basically everything you could throw at these types of problems. And none of these are even shown on this plot here because they all failed well before this point. And we really had to invent a new method based on this older work, which you could either ask me about or somebody in the front row about, for doing these sort of simulations with specifically sort of long-range one-dimensional systems with very high fidelity classically. So you can sort of see here that the standard MPS algorithm is much worse than even this improved algorithm. So we really think we have a good algorithm for doing this. The other thing I'll mention, coming back to this 2 qubit fidelity I talked about earlier, we can look at how the simulation time changes as a function of this equivalent fidelity. And you can see that for our current system of around 3 nines, this takes about 184 days. But as you improve this 2 qubit fidelity very marginally from 3 nines to 3 nines and 4, 3 nines and 5, etc., this time increases from 180 days to 100 years and very quickly approaches the age of the universe. So I'm not at all, to be very clear, claiming supremacy with our current experiment. But what I am saying is that we're clearly on the verge of analog quantum simulators surpassing what we can do with classical systems and being useful for actually studying the types of problems that they can address. And more sort of philosophically, I'd like to sort of point out that when supremacy experiments have been run in the past, they've always targeted these 2-dimensional complex random unitary circuits, basically designed to be as hard as possible to simulate classically. But what we're looking at here is time independent, it's global, it's one-dimensional evolution, basically the simplest type of quantum evolution you can imagine, and yet still classical computers struggle to keep up with. All of that, I think, is already interesting in of itself, being able to do this fidelity estimation, but I also think it's quite interesting that once you estimate fidelity, you can use that for useful applications. So that's what we're going to talk about in the last few minutes of my talk, are different applications of fidelity estimation. Before we go on, are there any questions about what we talked about so far, fidelity estimation, analog simulators, etc.? Yeah.
Amongst these many algorithms that you tried, are any of them like semi-classical algorithms, like compared to them?
I don't think any of them are semi-classical. I mean, I guess I'm not sure what you mean by semi-classical in this context. So maybe we can talk after about it. But I don't believe any of them are semi-classical.
And what you're saying that you're sampling, comparing this.
Exactly. Yeah. I'm basically here. I'm saying that we want to try to find some simulation method which is able to achieve a comparable global fidelity to our system after getting to a volume law entangled state for n equals 60. And my claim is that these ones here all fail well beforehand. And for instance, even methods that were used in Google's supremacy work like these sort of path integral, Feynman Schrodinger methods, actually don't work for our analog quantum physics because of the long range interaction. Okay, great. Application. So let's assume now that we can measure fidelity. What is that good for? Well, the first thing that we can do with the fidelity, is we can actually look at estimating the actual mixed state entanglement of the system. What do I mean by that? Whenever we talk about entanglement during this talk, I've been talking about pure state entanglement, the entanglement of this state psi. But of course, the state we actually produce an experiment is this noisy mixed state rho experimental. And generically, the entanglement between these two things will not be the same. But it's actually notoriously hard to even think about a measure for entanglement for mixed states, even theoretically. After browsing through lots of old works from the early 2000s, when people were thinking about these questions, we actually discovered that you could write down a very simple estimator for the mixed state entanglement, which is shown just here. Where the mixed state entanglement is just the pure state entanglement of the state here, plus the log of fidelity. Fidelity will be less than 1, so this quantity here will be negative, so mixed state entanglement will be less than pure state entanglement. You can actually prove that this is exact for certain states, so for isotropic states, and you can prove that it is exponentially tight as a function of system size for generic quantum systems, including ours. And we can show with error model simulation as well, it's an extremely good estimator. And so we can really, for the first time, show the actual mixed state entanglement entropy growth in an experimental system with up to 60 atoms reaching the volume one entanglement state. And does this really matter? It matters because we don't just have the opportunity to do this with Rydberg atom arrays. We can do this with any type of quantum system which can measure fidelity. And so, for instance, we can put on the same plot our experimental mixed state entanglement entropy against different types of digital quantum processors, and actually compare analog, digital, logical, hybrid processors all on the same footing. More scientifically, this mixed state entanglement entropy, which for the experts is a proxy for the negativity, is an estimator of how many bell pairs you possibly extract for your system. And actually, you can show that under very weak assumptions, it's a very good estimator of the classical simulation complexity of your system in a tensor network sense. So for these reasons, we actually think this is a very powerful benchmark for systems, and has now been taken up, for instance, by Google in their new work to actually show when their systems are computationally complex. So it's, I think, a very powerful tool going forward. Okay, that's entanglement estimation. What else can we do when we have a fidelity measure? Well, the next thing that we can think about doing is actually looking at, we can measure fidelity. How can we improve it? How can we learn the noise of our system? Before we go on there, any other questions about estimation? Okay, great. So we're going to think about how we can learn the noise of our system. To understand this, we're going to take a quick step back and consider a very simplified system, just random unitary circuits. And as we talked about earlier, if we have some randomized dynamics, like a random unitary circuit, and then we measure it in some fixed basis, then the distribution that comes out will be some random speckle pattern. And then as we talked about, the key fact of these random circuits or random ensembles in general is that if we look at the histogram of these probabilities, it follows this exponential probability of probabilities distribution. Key fact. The interesting thing is if you now introduce an error some point in the evolution, you still get a exponential distribution out. It's just that now this exponential distribution is an independent exponential distribution. This is a very key thing to emphasize, that basically whether or not there's an error changes this underlying probability distribution, but the histogram which describes these probabilities is still an exponential, no matter that an error has happened. So what we can think about is that we basically have two different options. If no error occurs in our system, then our probabilities will be sampled from some exponential distribution. If an error does occur in our system, we'll sample from a different exponential distribution, an independent exponential distribution. And in general, if we have sort of a space-time volume worth of error possibilities, we'll be sampling from one distribution with probability of F, many distributions with some lower probability. The key fact is that we can't keep track of all these errors microscopically. That's sort of the whole problem of quantum error correction, so we don't actually know what errors occur. And so this means that the actual distribution we measure at the end of our measurement is going to be an incoherent sum over all these independent distributions. And just to flash through the math facts very quickly, if you take an incoherent sum over these different distributions, you get something called a hypoexponential distribution, which is very well characterized. And the key fact about it is basically that this distribution is entirely parameterized by the noise channel that I chose in my experiment. meaning that given a noise channel, which I can just guess, or you can tell me in one moment, and a measured fidelity, we can always write down this corresponding type of exponential distribution, predict what the output will be, and then compare it against numerics or experiment. Yeah.
Sorry, the noise channel you're considering here is not a collapse. It's it's not like a measurement. It's just a random unitary.
Yeah, it's a random Paulian space.
Okay.
Okay. So why is this important? Well, what we can then do is the following. What I'm doing here is random unitary circuit simulation. And the bars, which basically look like fill to you in the back probably, the fill of the bars is the output from a numerical sort of open system simulation of random unitary circuits. So you can see those different distributions. The solid lines are analytical predictions for what those distributions should look like for different error models. So what you can see is that, for instance, for global depolarization, independent local errors, global Gaussian covariant errors, over rotations, under rotations, or some mixed arbitrary mixture of both, the distributions are clearly distinguishable from each other, and there's great agreement between the analytics and the numerical predictions. And then what we can do is we can apply this also to our Hamiltonian type systems, and we can see that the same great agreement persists in these cases as well. And I just want to highlight again, the fact we can even do these for Hamiltonian systems or any of these at all really comes back to this idea of periodically circuiticity, where we can apply ideas from random unitary circuits to the dynamics of analog quantum simulator systems. So with all that said, that's pretty much all I want to talk about today during my talk. I think the highlights of it are that really, as we move into the next stage of sort of NIST or beyond NIST quantum science, analog quantum simulators are going to be a very powerful tool for targeting specific problems of interest. And the ways we analyze them have to evolve and become more quantitative and more married to how we've typically analyzed digital quantum systems in the past. And that there are many different metrics that are universal across both analog and digital type systems. I want to highlight in particular my advisor Manuel, but especially also the long-standing collaboration between our group and Sunwon Choi at MIT, and in particular his student Daniel Mark, who really was sort of my co-collaborator in all of these works here. With that, thank you, and I'll take any questions.
As is our tradition, I believe in the first question or two come from
Can you give some intuition for this row diagonal? Yeah, some density.
Yeah, so this row diagonal, basically, you can write it in two different ways. The simplest way to think about it is that it's basically the time average of your state. And so in some sense, it's what your state looks like. If you take, it's like just, I'll say it this way and then I'll say it a different way. So first of all, it's diagonal in the energy eigenbasis. So basically, it's just a sum over all of your energy eigenstates with no coherences between them. And so it's really telling you sort of what is your population in the different energy eigenstates.
I don't want to.
It's your population in the different energy eigenstates. And that fact that sort of is directly telling you your population in different energies is the reason why it's able to do these things.
Fancy words, yeah, they use a lot of fancy words to describe something that is.
I don't know if I'm speaking.
I think we need someone on that. Does anyone know how to do that?
That's what I think. At least this is Ergo the city. I don't know what Ergo is. That just means you have completely noise, no information. You enter.
We muted.
Yeah.
Okay, I think we should just speak up and pretend that there's not a conversation.
If you're on Zoom, please mute.
I think everyone is muted now. So
Okay, other questions?
It's a quick follow-up, but like, can I think of this like the weighting my P as like just importance sampling? Or
No, I don't think you can think about it that way. What you should really think about it is that essentially what I'm saying is that you take any observable of your quantum system, right? And that observable over time will have some fluctuation, right? It'll have some average value, but it'll have some variance, it'll have some kurtosis, it'll have some higher order moments of that creation. What I'm basically saying here is that if you tell me just the average value of basically any quantum observable, that average value uniquely defines all of the higher moments. So the average value uniquely defines the variance, it uniquely defines the third moment, etc. Because what you can break the evolution down into is the product of that average value, this p diagonal, and then these universal moments from the random state ensembles. So it's not like it's just important sampling, it's really sort of telling you something fundamental about what is the, way you can break up how a state moves. Does that make sense? Not.
Yeah, I think we're.
Sort of like, well, like a squeeze state, how would the mean define the variance when it's different in two directions?
Well, so this is like,
I'm seeing it over time.
this is evolution over time, right? So this is looking at, like, if you take some state and you evolve it with some dynamics, and then you look at how those dynamics change over time, then it holds. But you have to tell me the Hamiltonian that my squeeze state evolves under for me to tell you that this is true. It's just like a squeeze state is not a sufficient information because a squeeze state doesn't define this p diagonal. That's just like an initial state that I put into my Hamiltonian evolution.
So you talked about a new measure of entanglement entropy or a bound on
Yeah.
how much of the entanglement entropy comes from pure state entanglement entropy. Could you explain that a little more?
Yes. So, yeah, I can unplug here. So I'm gonna unplug so the next one can get set up, I guess, but essentially all that we're looking at here is that if you look at the pure state entanglement, and you then basically look at the most intuitive way to think about it is that if your noisy mixed state, bro, has high overlap with your pure state, then you of course expect to have similar types of entanglement. And what you can then prove is that if your pure state psi is sort of any eigenstate of your noisy mixed state, it sort of has enough similarity to your noisy mixed state, then you can show that this formula holds with this exponential type bound. And we can then show that there are sort of looser but still exponentially type bounds this holds for more generic states, even when the psi is not an eigenstate of your rho. So the point really is that you should think about this as taking the pure state entanglement entropy and then just adding this cost based on some error offset from it.
Okay, so this metric is specific, it's not for a generic mixed state, it's for a mixed state that you know is quite close to some pure state you're attempting.
It holds up to a fidelity of 1 over square root of the Hilbert space dimension, so it can be quite a low fidelity overlap.
Okay.
But yes, it only holds for 1 over its Hilbert space dimension. But for n equals 60, for instance, that's a fidelity of like 10 to the minus 8 or something like that. So it's not a regime that we care about.
Right, thank you.
Okay, so let's thank Adam again.
For our second talk, I'm really happy to introduce Merrick Long, our newest theory block firm postdoc fellow. David got his PhD with Transmon at Boston University and was at KQI Merrill Long before joining us at Stanford. David's done many really nice works on many body localization, driven system, classification of topological phases, and today he'll be telling us about some of the more experimental aspects.
Good introduction. Yeah, so I guess the previous talk was experimentalist talking mostly about theory. This talk is going to be theorist, but mostly about an experiment in a group of Alicia Ola at the University of Maryland, who was in fact a Stanford alumni. But maybe the real hero of this talk is going to be Martin Ritter, who was the student at University of Maryland, who was leading the charge on this work that I was mostly at UMD, and he was kind of backed up by Billy, who's another student at the theory side. He and my former advisor. So this talk is going to be about the stabilization of a periodically varying Floquet state in like a simple quantum system of just a qubit coupled to a cavity, specifically superconducting transmon qubit. And the selling points of this work is that we are going to be able to stabilize this Floquet state, so it's not going to suffer from any kind of decoherence on long time scales. It's going to be like a quantum state which is nearly pure and which just like lives essentially for like beyond any time scale that will be relevant for what I'm talking about. And this scheme that we're going to use to stabilize this time and periodic state is going to be particularly simple. It's not going to require any kind of detailed control of any kind of like dissipative elements in the system. We're just going to couple a qubit to kind of a simple lossy cavity and just turn on static coupling, and by sufficient control of just the qubit alone, without touching any of the couplings, we will be able to stabilize this Floquet ideal state. So we don't need, in particular, we don't need any kind of measurement or any kind of feedback, which is why I'm going to call this thing phonics. It doesn't require input from us. You just kind of flick the switch on like the microwave generator, and it would just go to this interesting thing. And then kind of the theory component is going to be the explanation of like why does this work, and then kind of extrapolating beyond regime that the experiment can access. So I'll begin with like some motivations, like why would you want to stabilize these time varying states, these Floquet states from the period project. So one of the big motivations is this field of Floquet engineering. The idea is that you can engineer effective interactions in some kind of rotating frame by introducing a periodic drive to a system which natively would not have these kinds of interesting interactions by itself. So one example of like a state that people would very much like to compare, and like how much training people would like to realize in their quantum simulators is this adiabatic model. It's from like a theory point of view, I guess it's a pretty simple Hamiltonian. It's got three different kind of flavors of interaction terms, two-body interaction terms between qubits sitting on the vertices of a hexagonal lattice. It has these anisotropic interactions, being like a VZ interaction on the vertical links, XX on the one of the orientation, diagonal links, and YY on the orientation of the diagonal links. So while kind of theoretically this looks like a simple Hamiltonian, having these kinds of extremely anisotropic interactions is something which is actually kind of hard to engineer, even on these kind of like well-controlled quantum simulator platforms. So kind of just natively having a Hamiltonian like this is like not so easy. But what you can do is you can instead do like a sequence of pulses in your Hamiltonian. So you can have a time varying Hamiltonian where you're going to turn on a ZZ interaction for a short amount of time, like a third of some period, and then turn on an XX interaction for some next third of the period, and then turn on a YY interaction for the remainder of the period. And you do this kind of cycle between these very quickly, and then there's some rotating frame transformation, which will take you to a high frequency, like in the high frequency regime, will take you to an effective Hamiltonian, which is just this adiabatic. Right. So the story is that you start with these ZZ interactions, which you can do. You can do these XX interactions, you can do these YY interactions all kind of independently. And you cycle through them fast enough, and you get this interesting topological okay. So if that were the end of the story, then this would be the secret to doing topological quantum computation. You can all go home, start a startup, and have money. You're all invited. Unfortunately, this is not the end of the story. What you want is not really just this like effective Hamiltonian. You want the ground state of this. And so, okay, in preparing like quantum states, there are certainly some quantum states which are easy, which are the ground states of gap Hamiltonians. All I need to do is put my system in a fridge, and then the system will kind of slowly make its way down to the ground state as it gets fuller. And this will let me compare the system in the ground state. Unfortunately, this fridge does not play well with this rotating frame transformation. So what can look like cooling in the lab frame when you're like applying these pulses can really look like heating, or like something even not necessarily like a bang beta bounce, some kind of like highly energetic process in the rotating frame. So I'll go through like some detailed examples as we like come to the experiment, but like maybe you can already see it here. Like in the lab frame, the ground state of this this lattice is actually just like every qubit like in its ground state. So like in the in like the ground state of like some kind. So just like a product state. Every qubit is just going to be sent to a particular state, called the zero state, in a computational basis, and that's like what this tooling kind of wants to do. That all zero state is not the ground state of this effective Hamiltonian. It's some like highly excited state. And so that's why like this fridge can look like an oven in this effective Hamiltonian. So what we're going to be trying to do is finding a way to basically do cooling in this time varying rotating. And like not the first people to like consider this problem. There have been many works previously, including by like, the audience, on getting stabilization of like arbitrary states in quantum systems. And what's going to distinguish what I'm going to talk about today from like, that previous work is really that we're going to be talking explicitly about these like, Floquet states, which are really like varying as a function of time. So we're going to be wanting to like follow them along throughout the period. Okay, so we can probably make that more explicit by going through some like, minimal example of just the driven qubit, which is going to be also the experiment that we'll be considering. So a system is some qubit, it's got two levels, I'm going to call it the ground inside, and we're going to apply to this qubit a strong circularly polarized drive, here by this the arrow, and more precisely this Hamiltonian, so it's cosine times sigma z plus sine times sigma x. And our qubit also experiences some like uncontrolled loss, right? Some like relaxation from the excited state down to the ground state. Time scale, which is going to be this t1, and so the rate is going to call gamma, which is 1 t1. Okay, so what is the state that we want to stabilize in this Hamiltonian? I want to stabilize the so-called Floquet states or quasienergy states of this Hamiltonian. But let me just consider the regime where this driving frequency is very small, and then I won't have to talk about quasienergy or anything. I can just talk about the instantaneous eigenstates of this Hamiltonian. That would be enough to really get it started. So what are the instantaneous eigenstates of this Hamiltonian? Here I'm drawing some cross-section of the box sphere. On the y-axis is the expectation of sigma z, the x-axis is the expectation of sigma x, and at time equals 0, my Hamiltonian is just sigma z. So the ground state is the state of like minus sigma z. Right, so my ground state in the box sphere is coming down at time equals 0. At time equals a quarter period, my Hamiltonian is plus sigma x, so my ground state points at the left on the block sphere at time t on 2, so 1/2 of a period. My ground state of this Hamiltonian is actually the excited state in the lab frame, right? So I'm now saying that like the Hamiltonian that I want has a ground state which is actually like exactly opposite of the ground state of this qubit like back in the lab. So you can see that like this loss, which sends me from the excited state down to the ground state in the lab frame, is actually going to look like heating in this effective like rotating, right? Because it's going to take me from my excited state, which in the instantaneous frame is really like the lowest energy, and take me down to like in the lab frame, the ground state, which is really the highest energy. So that's a way of seeing what I said before about like cooling in the lab frame and the heating to gate states. And then as we go further along in the period, the gate state continues to rotate around the sphere until it eventually comes back to itself. And so this is the state that we would like to stabilize. I'm going to call it phi minus of time, and it's really this time varying state which kind of spins around the box sphere like this. Everyone needs to be very impressed by that. Okay, so this is the state that we want to stabilize.
Does that mean in Blender?
This was made in PowerPoint But it's not apparently, I don't know.
Can you do it again? I missed.
Yeah. You can do it as many times as anyone wants. There you go. Yeah, it's apparently not an animation which exists natively in PowerPoint, like you need to combine two different animations.
So was the movement of the back end, is that Floquet micro motion?
In fact, this is what I can't like create a perfectly concentric surface in PowerPoint. But, like, we can say it's not.
Okay, I did this, you have 25 minutes total.
Yeah.
Yeah.
Yeah, so this is what we want to do, this is what we want to say to this. And the secret sauce is going to be this this cavity that we're going to connect the system to. So, but like really like nothing else. It's like we're going to put this system in a lossy cavity with some photon loss rate kappa, and this will already, by the judicious choice of this P0, so the amplitude of this Hamiltonian, so circularly polarized drive, will send us to stabilize the state. Okay, so what is the experiment? In practice, as I said, some superconducting transmon qubit. Here is the CAD of that thing. This looks like a few components. It's got this kind of microwave drive line, which delivers this sigma x part of the Hamiltonian, so it transitions between the Z and the E state. It's got some flux bias line to zoom in here, which can change like the frequency of the qubit, so it changes like the splitting between the G and the E state. So it controls this Z. It's got some resonator, which is going to be this lossy cavity that's going to give us the stabilization of the Floquet state. It has the frequency with delta, which is the feeling between the qubit and the cavity. And there's some coupling between this cavity and this photon loss rate kappa in the microresonator needs to figure the qubit law. Okay, so what is the results? And then we'll walk through and like understand what the origin of this effect is. So first we're going to orient this by seeing like what was the effect. We're going to see that we get the stabilization. So I'm going to start kind of with a large detuning. So this is the detuning between the cavity frequency and the amplitude of the drive on the qubit, which is really like the qubit energy, because it's a circularly polarized drive, but the instantaneous splitting between the instantaneous like line and anti-line state with the field is always the same. It's a circle rather than ellipse. So this is like the instantaneous energy of the qubit, and this is the cavity, not driven. And if we have these things being far detuned compared to the coupling between the cavity and the qubit, then what happens is if we plot the probability of being in the excited state as a function of time, both for initial starting in an initial state, which is this phi minus state that we want to stabilize, but also the opposite state, phi plus, so it won't be in the direction of the box here. You can see that both of these things kind of oscillate out of phase, but then they decay and to something which is like just a little bit biased on 50% probability of being in the excited state. And there's some characteristic decay time for that process.
And then decay time is set by some loss.
Yeah, it's comparable to this T1. Yeah, it's maybe interesting that it's significantly longer than T2 for the qubit, which is like the phase coherence time. And we suspect that that's due to like the presence of this like strong driving field kind of suppressing the influence of like small fluctuations in frequency, which would be the result, which would probably be giving you your okay, so then let's move a little bit closer to like resonance between the cavity and this qubit. So we're now like kind of two coupling constants away. And we can see that let's first focus on the blue curve, which is the aligned state, or the state that we would like to stabilize. And we can see that, yeah, it's like not really decaying all the way to zero. Like even out at these kind of relatively longer times, we've still got these like persistent oscillations in this probably being in the excited state. And this is a signature of us like following along this circle in the block sphere. So our state is really like following this Floquet state as a function of time. And kind of maybe more interestingly, if we start in the opposite state, so we begin out of phase, we're following the opposite state around this circle, we kind of first decay, you like lose kind of contrast with these oscillations, but then these oscillations pick up again as we start to pull into this opposite state, which is circulating around the block sphere. So we started in the opposite state, but actually our cavity is kind of taking us into the state that we want to end up. And if you move even closer to resonance, then you can see that these oscillations kind of go on, as long as you care. It's like 100 microseconds. It's like 10 times any of the intrinsic loss rates in the qubit or in the cavity. Like you've still got these kind of coherent oscillations. And here's like the qubit T1 for reference. Okay, so why is this? Here's the explanation.
Sorry, can you go back?
Yeah.
So this is your, so by doing this well-chosen right coupling, you're saying you can make this qubit live forever instead of having the qubit.
So to be clear, it's a particular state. We're engineering the steady state is this non-trivial pure state, which is like oscillating as a function of time. There's no like protected two-level subspace.
So this is like for T1, but you just have like depolarizing noise which is affecting you. Does this still work?
Yeah, it should work for anything which is like, so long as the uncontrolled noise is kind of weaker than the loss in your cavity, it shouldn't matter at all. It should kind of perturb the amplitude of this thing, but like that will be basically following this Floquet state. It's going to be. Yeah.
Sorry, so what is your Floquet state here? Is it like the superposition with the counter-rotating waves, or is it like that?
It's that. Yeah, so it's the state which is like kind of oscillating through the block sphere as a function of time.
The oscillation is within the period, that's my.
Yes.
So the point is you want to use Floquet engineering to get desired states,
Yeah.
but usually that's subject to either dissipation or Floquet heating.
Yeah.
And like, if you figure out a way to counteract all of that.
Yeah.
To use Floquet engineering to get your desired state and have it live there.
Yeah, exactly. So like there's no like natural kind of notion of cooling in the real Floquet systems, right? You can like start putting on this drive and generically your system is like gets hotter and hotter and hotter. But here is a way to make your Floquet system actually cool down to the ground state and make it steady. Yes.
On our the experimental data, you only show the oscillation of the excitation. You also see the X and Y excitation.
You can. They're harder to measure, and I don't have them in the slide deck, but you can do that.
But how do you know is it true?
So for maybe something which is like even slightly better and easier to measure is that you can actually like directly measure the fidelity between this like circulating state and the actual state realized by your experiment. And the same kind of like envelope thing, if you kind of tracks this fidelity basically going to like a constant value of 1 as a function of time. So this would be like directly investing. Both shows that it's pure and that it is in fact state. Yeah.
Is the reason that the cavity cooling still works basically because you can, when you go into this rotating frame, you can just make this into like a more detuning on the cavity, so the cavity doesn't really care about the rotating qubit versus the sort of static B field.
I'm not sure I understood the question, maybe because I couldn't quite hear. But I'm about to give the explanation, so maybe just like ask again if it's not clear after that. Yeah, okay, so on this plot over here, I've got the energy of the qubit. Remember, like the energy of this qubit, because it's of this like circularly rotating field, it actually doesn't change the function of time. But the energy of this phi minus state is constant, it's minus d naught on 2. Phi plus is also constant, plus d naught on 2. Let's first understand this is a wrong caption. This is not what the tuning is, but now. Let's first understand this plot where things were decaying. So why did this happen? It just happened because these cooling processes in the lab frame can be heating in this Floquet frame. So we have not just like transitions from phi plus down to phi minus, we actually also have transitions from phi minus up to phi plus. So we end up with this final steady state, which is kind of mixed and between the both of these things. Okay, so that's, yeah, it's having heating in the Floquet frame. Okay, so now let's move a little bit closer to resonance. We've still got these processes which are sending us between these two instantaneous states. But now, because of this cavity, so on the x-axis, I'm plotting the cavity occupation and like different states associated to like being in the phi minus state of the qubit, but having one photon in cavity. Which is like phi plus on the qubit, but having one photon in cavity. And what we're doing is we're moving closer and closer to having a resonance between this excited state of the qubit, but no photons in the cavity, and this phi minus state on the qubit, like one photon in the cavity. And so there's some coupling G between these two things. It could mean that if I've got a qubit which is like living in this state, it can kind of like flop into this state. But then there's this cavity decay process that we've like put in, which will let the cavity decay from having one photon down to 0, and that will put us back in this phi minus state. So what it means is that like maybe there'll be this process which kind of picks us up here, but then very quickly we flop over here and come back down. So that we kind of end up pumping down into this state, which is this phi minus state. And for the many introverts in the room, this like triple of diagrams should just look like optical pumping because that's what it is. But it's optical pumping of these Floquet states. So that's like really the thing which we're managing to do is that we're showing that you can do this like optical pumping protocol, which is like ubiquitous, but actually you can do it with these quasi-energy states, these Floquet states, which like varying it. And as you get closer and closer to resonance, then like, this plot starts going on the screen. Stabilize into the state. Okay, and so there's like additional like modification to this theory, to this explanation, which kind of tells us that it should work even outside of this kind of like slow driving regime where you're just talking about instantaneous states. And that's by like, again, like it's like really taken seriously that these Floquet systems don't really have like a conserved energy. They can absorb energy from the drive. So they only have this conserved volume, which you should really just think of as being like energy modulo the frequency of the drive, because there's like photons coming in from the drive, which can like push me up and down in my energy by like h bar omega. So that there's a technical definition, it's a quasi-energy state. If you have like a periodic solution of the Schrodinger equation up to a global phase, and that global phase is the quasi-energy. But you should really just think of it as being like a level diagram where we now have a bunch of copies of these states, which are like separated by this energy decoding. And so the kind of brief statement is that everything I outlined with this optical pumping of Floquet states works also for these quasi-energy states, where I just like cross out energy on the y-axis and I replace it with quasi-energy. Okay, and we can confirm that maybe numerically because experiment would have a hard time getting to kind of regime where you would be able to test that. in this fluid simulation. What is this plot showing? Here, I'm plotting on the vertical axis the detuning between the qubit and cavity, so that's this delta. And on the horizontal axis, I'm plotting this frequency of the drive. I guess here is omega mod for modulation. And on the color map, I'm showing the fidelity between the steady state of this like driven dissipative system and the quasienergy state belonging to this epsilon minus in this diagram. And we can, and this plot is marked by these lines, basically the resonance conditions between these quasienergy levels. So for instance, there's this kind of direct resonance where this epsilon plus quasienergy is resonant with the epsilon minus quasienergy plus the energy of the cavity. And that belongs to like this line, and you can see it lies right on top of one of these like peaks in the fidelity. So this is telling us that when we meet this resonance condition, we really stabilize into this quasienergy. And there are like higher order versions. So here it's shifted by omega mod, where we like become resonant with one of these other Floquet copies. And you can see that also there's a peak there. So this is really like telling us with a numerical confirmation that really the condition that matters is a resonance between these quasienergies. And I will also point out that you don't actually need to know what a quasienergy state is. You just need to like scan until you get one of these resonances, and then you'll know that you're stabilizing into one of the quasienergy states of the system. And there are like still like other kinds of higher order processes where you have two photons, but like no Floquet copies, and these also kind of turn on in this plot. Okay, so that's the explanation of this effect. What we've managed to do is stabilize these Floquet states, these quasi-energy states of periodically driven qubit. We have like reason to believe that this should extend to like many-body systems and like ground state I outlined at the beginning. I also think that there's kind of an opportunity to think about what you can do with these like really like strongly varying stabilized states and like using them as resources for like classically difficult tasks. Like right now there's like a well-developed theory of like having these like resource states which are static. And I think that maybe there hasn't been like such motivation to think about resource states that like vary as a function of time. But I do think that there's opportunity there to get new kinds of processes and new kinds of take it. Right, I'm happy to take any questions.
Okay, start with the student question.
Are there limitations to what you want the coupling strength between the cavity and the transmon to be the T value? It seems like the higher you go, the better.
If we look at this diagrams. So the coupling between things, it should not be so large, it's like so it needs to be like smaller splitting of a bit. But that should be okay. And it should be larger than this. It's like large. Between those two limits.
Yeah.
That's
It's going to be
Merit that determines how well you can do.
This fidelity is probably all right. So this is like the time average overlap between the actual like steady system and like a lot of positive thing. We'd also consider like the time it takes to go to that. But I mean, that's supposed to be choose the fidelity.
How does that scale? Like if you're allowed to do any coupling that you want to line with that you want, what sets the fidelity you can achieve?
Like what the relationship between those things is, and
But I'm saying, you're allowed to pick them to be whatever you want to define for fidelity and what limits your fidelity. Reason I asked,
It's not clear to me that there's like a limit other than one.
I mean, but you said G changes big enough, then it's like coupling to other states.
Yeah, but you're allowed to like pick that as well, right? Like if you're really allowed to like scale up.
you're not allowed to change your system, but you're allowed to change it at the. So I'm saying you have some physical system, but you want to dissipatively stabilize it.
Yeah.
And so the question I guess I then asked is like, if you give me this, if I give you the system parameters, can you tell me how well I could possibly do with this kind of location?
So you're allowed to have
You can pick the cavity coupling to be, I'll build that to be anything I want, you know, in circuit QED, I can make it whatever you want because Dave Schuster's doing that. And they're good, and they can make a cavity line with it.
Yeah.
But the question is just like, I have some system, what kind of fidelity am I getting, could I possibly hope to get?
Yeah, I think it's. I think the optimal values are when like the coupling and the cavity line width is comparable, but when you're in that regime, like the fidelity is quite close to one. Like I don't think that I know exactly the value here on this peak. But I do think that like it's set by like the difference between like the cavity loss and like the qubit T1 like lifetime, right? So like if you can make if you can like simultaneously have like operate in this regime where like you like have this nice steady resonance, your cavity loss is like still very large. So I guess if you this study is larger and larger to remain in that regime, then I don't think that like I think you can this approach one.
That's why this would break the main problem. Then it's.
Yeah, so for many body, there's like a couple of wrinkles. There's not just like you'll only actually have to stabilize like an isolated state. There'll be like some like big nets of things up here, and you want to like kind of clear out all of this stuff like cavity. And I guess we're still thinking about like how exactly that should be done, and like what will limit it, but you have to imagine that like the limits of much.
Great, let's thank David.